All right, good morning, everyone. First thing I want to announce is that I apologize for the scare, but nobody contacted me about the homework due date being yesterday. Homework 10, if you recall, on Monday, I kept repeating, saying that mesh current analysis as a topic has been introduced. I will cover the example in class on Wednesday, and I will make the homework due on Friday or Saturday. And no, no one informed me that it was due yesterday. Now, I'm not saying it's a student's responsibility, but if you remember, I said the dates on Pearson are a placeholder because if I don't put a due date on it, the assignments are not visible to the students. So I put a placeholder date on there just so at the beginning of the quarter, all the assignments are available to the students. Okay. So the actual homework due date for mesh current analysis is not until Saturday. Okay. So I mentioned this in class on the first, and then in the 9 o'clock class, some students then informed me that the due date was set at yesterday. But again, I stated this very clearly in class on Monday that the homework will not be due until Saturday. Yes, you're ahead. Yeah, and several students did it, so I was kind of like happy about it. But then the students pointed out that it was due yesterday, and that's why a lot of them had finished it homework. But again, as I said, I stated there, and I know it can get confusing. You're taking multiple classes. There are multiple rules, multiple different assignments from different professors in different classes, so it can get confusing. But in my class, again, homework due dates are a placeholder. It is not, the due date is not finalized until the topic is completely covered in class. And so mesh current analysis, we talked about it on Friday. We talked about it on Monday. So students can open up the homework, but it's not completely due until the topic is finished in class, which we're going to do today. All right, so let's go and look at the example for today's class, mesh current analysis. Where did it go? Oh, there it is. Right. In section 4. No, shouldn't be this. Maximum power transfer theorem. How did it go this far ahead? Okay, there you go. All right, so summary of the steps. The first thing to do in mesh current analysis is to identify all the meshes, assign mesh currents, and choose a direction for the mesh current. To keep things consistent and simple, always choose a clockwise direction. Okay. Always choose a clockwise direction. And there's a reason for this. It will become clear once we do the example. All right. Then you apply KVL to each mesh, then use Ohm's law to express each voltage in that mesh as a function of that mesh current. So you sum up the voltage in the mesh, and the voltages, of course, can be written as V equals IR, where this I is the unknown quantity that you have to solve, the mesh current. All right. So let's take a look at an example. Solve for all the mesh currents and resistor voltages. We'll solve for the mesh currents, but not all the voltages. Okay. 3 voltage sources in there, VA, VB, VC, and 4 resistors. VA is given to us as 10 volts. VB is given to us as 9. VC is 1. This is 5. This is 5, 5, and this is 10. 2 meshes to identify, easy enough. I will choose a clockwise current, IX and IY. Mesh 1, mesh 2. I already have 1, 2, 3, and A, B, C in there. So just X and Y. You can choose whatever you want. All right. So now, first step is done. Assign clockwise direction. Assumed 2 mesh currents, IX and IY. Now we apply KVL. Okay. Mesh 1. KVL in mesh 1, simply summing up the voltages around the loop. 4 voltages, VA, VB, VR1, and VR2. As always, I start in the bottom left corner of my mesh and go clockwise while summing up the voltages. So I obtain minus VA plus VR1 plus VB plus VR2 equal to 0. Okay, I'll wait while students write it down. So far, so good. Then apply Ohm's law. VA, of course, is known, but we'll wait. VA, then VR1 can be expressed as IX times R1. VB also is a voltage source. VR2 is IX minus IY times R2. Okay, IX minus RY times R2. Now, explanation for why it is IX minus IY. Well, at the beginning of our analysis, we chose IX and IY to be both clockwise. Because they are clockwise, R2, which is a shared branch, has IX going down and IY going up. So it causes a voltage drop in this direction for each respective current. So when you are in mesh 1 and you add up those voltages, IX would be positive, IY would be negative, and hence IX minus IY. This will be balanced when we get to mesh 2, and in mesh 2, IY will be positive and IX would be negative. So you would get IY minus IX for the exact same resistor voltage. Okay, that's why in the previous slide, I stated, always choose clockwise direction for all of your mesh currents. And then when it comes time to apply Ohm's law, you can simply take the current in that mesh to be positive and the current outside the mesh as negative. And that's it, straightforward. Again, it bears repeating. This is a non-EE major class, right? This is a class for non-EE major. So you're learning analysis techniques. These are all tools in your toolbox. You should know how to use each one of these tools. Okay. It is not important to know how the tool was manufactured, how it was built, where the raw materials came from. It's good to know, but it's not important to know, if that makes sense. So there is an explanation. I did go over the explanation in class. If you recall, I talked about this, right? We have two voltage drops in there, plus and minus and plus. But to keep things simple, when you want to apply mesh current analysis, you just follow this technique. Choose clockwise directions for all your currents. And then when you apply KVL to a mesh, that mesh current is positive. The current outside the mesh is negative. And it comes from the fact that you have currents going the opposite direction. Does that make sense? Any questions? Okay. Once you have this, you plug in all the known values. VA is 10. So minus 10 plus 5 times IX plus 9 plus 10 times IX minus 10 times IY is equal to 0. Reduce the equation in the form of AX plus BY is equal to C and rearrange the terms. So I obtain (15IX) minus, what did I miss? Minus 10IY is equal to 1. So minus 10 plus 9 gives me minus 1. Take it on the other side. I get 1. And I will call this and label it as equation number 1. And that's it. Equation number 1. Then move to mesh 2. Mesh 2, I apply KVL. I have 5 quantities in there, 5 voltages, 2 voltage sources and 3 resistances. Out of those 3, 1 R2. VR2 is a shared branch caused due to 2 currents, IY and IX. But this time, since I'm applying KVL to mesh 2, IY is positive, IX is negative. And so VR2, the same quantity, is now written as, well, actually, let me first write KVL. So I have VR2 minus VB plus VR3 plus VC plus VR4 equals to 0. The same VR2 is now IY minus IX times R2. IY is positive, IX is negative. So it becomes IY minus IX times R2 minus VB plus IY times R3 plus VC plus IY times R4, 0. Plug in all the known values. And I would get 10 times IY minus 10 times IX minus 9 plus 5 times IY plus 1 plus 5 times IY equal to 0. Reduce the equation to a linear form, AX plus or minus BY equals C, and I obtain what do I obtain? Minus 10ix plus 20 times iy is equal to minus 8, goes on the other side. I get 8. Call that equation number 2. Two unknown variables, ix and iy, two mesh currents. So I need two equations. I have my two equations. Solve them using any method you're comfortable with. Solve them manually, plug it into your calculators, or use an online solver. Doesn't really matter. A note about using online solvers: while you're taking a quiz or homework, you can use online solvers. But in the final exam, you're only allowed an equation sheet and a calculator, and you will be doing this on paper. No digital devices. So you will not have access to the internet. You will not have access to an online solver to solve these kind of equations. So as engineers, you should be able to solve these. I would not give you anything more than 3 variables. More likely it was going to be 2 variables, but definitely not more than 3. So you should know how to solve these using your own calculator devices. Yes. Programmable calculators is fine. Right? So I know the TI, 84, 84 plus, they're the most popular ones. I think most ones have those. You can program 3 equations in there, spit out x is equal to this, y is equal to this, and z is equal to this, A, B, C values all at once. But again, as engineers, you should know how to solve these manually. This one's easy because it's only 2. If you have 3 or more, you can use matrix determinant method. You can solve it that way. This one right here, I would say, let's say multiply equation 1 by 2 and equation 2 by 3. That would give me 30ix minus 20iy equals 2. And this is minus 30ix plus 60iy. Actually, I didn't need to do that. 24. Summing it up, I get 0 plus 40 times iy equals 26. Therefore, iy is 26 by 40. 11.65 amps. If I just add the other two equations, I can automatically get, let's see, what do I get? 20ix is equal to 10. And so ix is equal to 0.5. All right, there's a procedure and the steps make sense. Straightforward enough, right? The circuit looks a little complicated at the beginning because you have 3 voltage sources, 4 resistors, seems like 7 components. Might be tricky, but it's rather straightforward. Mesh current analysis in general, I find, is a little straightforward than node voltage analysis. Okay. But depending on the circuit, that could flip. Okay. It is up to you as an engineer to decide which method you want to use. I mean, in class, obviously, I'm going to ask you a question specific to node voltage or mesh current. But when you're out working in the industry as an engineer, you have to decide which is the most efficient and the least expensive method for your problem. Okay. You could solve this with node voltage analysis, So the way to determine this is to determine how many unknown variables you would have. If you use node voltage analysis, how many nodes do we see here? At the bottom node, right? So we have the bottom node right there. That's one. We can choose that as the reference. Then you have 1, 2, 3, 4, and 5. Everywhere you have a junction is a node. So if you choose node voltage analysis, you have 5 unknown variables. Make sense? So you need 5 equations. Mesh, there's only 2. 2 unknown variables, 2 mesh currents. So mesh current analysis is more efficient than node voltage in this case, right? No. Okay, any questions? Any questions at all? All right. So then let's find the current through R2. And I'm choosing R2 because it is a shared branch. Okay. You have IX coming down, which is 0.5, and you have IY going up. It's 0.65. Mesh currents are not real. They are hypothetical. They are theoretical. Right? You cannot have 2 physical currents going the opposite direction. Hypothetical current IX is going down, IY is going up. So what is the real current flowing through R2? And which direction is it flowing? Yep, 0.15 amps going up. In this case, you do not have to look at the circuit. Okay, do not look at the voltage polarities for the sources. Do not look at anything except for this resistor, this shared resistor in isolation. You have 2 hypothetical currents shown to you, and you have 2 values. Whichever is the larger value wins. Well, for lack of a better word, wins. So IR2 is simply IY minus IX and 0.15 going up. Look at that resistor in isolation. Whichever is the larger value for those mesh currents, that is the actual direction for the actual current that branch. Even if both were minus, you would still pick the larger value. So if it was minus 0.5 and minus 0.65, then IX would be larger. So again, simply look at the numerical values. Not look at anything else. Yes. Yes, not the magnitude. Not the magnitude, along with the sign. So minus 0.5, yes. Minus 0.5 would be, well, I was going to say larger. But I haven't seen many examples like that. Typically for a quiz or a final exam, I just randomly draw out circuits. So I wouldn't know the solution myself until I actually sit down and solve it. So it is possible that we might have a case like that come up, just because of the way I might design a problem. All right, any questions? Method makes sense? Concepts clear? Okay, so this was a resistor that was shared between 2 meshes. What if we have a what if we have a current source that is shared between 2 meshes? We'd call on Marvel, some of the Marvel superheroes, because we'd have to have a super mesh. Lame jokes. That elicited more laughter. What was I saying? Oh, super mesh. So we combine the shared branches. We combine the two meshes which have the shared current source, and we combine into super mesh. We draw a loop around both meshes, and we remove the current source. But essentially what you're doing is simply applying KVL around the outer loop. That's it. So I explain in words, but essentially what you're doing is as simple as applying KVL on the outer loop of those meshes. That's it. So compared to a super node, super mesh is rather straightforward and easy. All you're doing is you're applying KVL around the outer loop of those two meshes together. Yes. Yes, you can, but we would not be able to describe the voltage across that current source. So we would say, okay, the 5 amp source, let's say, has some unknown voltage Vs, and we apply KVL around mesh 1 and then mesh 2, we'd have Vs in both our equations, but we'd have no way of describing that Vs voltage. So if we cannot describe it, we eliminate it. This concept and the derivation is exactly the same as the supernode, but essentially it boils down to applying KVL on the outer loop of those two meshes. That's what it boils down to. So applying KVL on the outer loop. What do we have? The first thing you should know is that you do not choose a new mesh current. The mesh currents that you have already chosen for both I1 and I2, they remain the same. You do not choose a new one. Okay. So starting from the bottom left corner, I have the 1 ohm resistor. So I have I1 times 1. Then I have a shared resistor. The 2 ohm resistor is shared. So I would have I1 minus I3 times 2 plus I2 minus I3 times 4 plus 10 equals 0. So 10-second pause while you write it down, think over it. Let me know if you have any questions. Any questions at all? Yes. Because I apply KVL in the clockwise direction. And so my technique is always whichever voltage I encounter and polarity first, that's plus. If it's minus, then I put minus. If this was flipped, then I would encounter minus first, then I would put down minus 10. If I sum up the voltages in this direction, then I would get minus 10, minus 4, minus 2, minus 1 equals 0. Essentially the same equation. Does this make sense? Super mesh. All you're doing is you're applying KVL on the outer loop of the two combined meshes. You combine the mesh, but you do not combine the mesh currents. The mesh currents still remain the same. If you do that, then your answer will be correct. If you don't do that, then your answer will be wrong. So that was super mesh. You can still, like R2 was shared, and we described IR2 in terms of IX and IY. We apply the same principle to that current source and generate an equation for that current source. I can say 5 is equal to I2 minus I1. Current source 5 amps is going in the upward direction, is going up top, is going up. I2 is also going up. I1 is coming down. So essentially I could say I1 is 5 plus I2, or 5 is equal to, oh, did I get it right? 5 plus I2. Oh, no, it's a difference. Yeah. I2 minus I1 is equal to 5. That is correct. As I tend to, I was overthinking. I2 minus I1 is equal to 5. That's the relationship we can write down. And from that, we can write I2 is equal to I1 plus 5, or I can write I1 is equal to I2 minus 5. That's the right equation. So here we have three variables, I1, I3, and I2, right? I1, I2, I3 are all present in this equation. We can substitute I1 in terms of I2, right? We can substitute I1 in terms of I2, or we could substitute I2 in terms of I1, thus eliminating either one of these. So from three variables, I1, I2, and I3, I would be down to only two unknown variables. Does that make sense? Right? We substitute, or we plug in I2 and I1 in terms of the other mesh current, plug into this larger equation. This larger equation will only have two unknown variables. So we take this and we can plug it here. And then, of course, you apply KVL to mesh 3 up top. So this is M1 plus M2. You apply KVL in mesh 3 up top, and you would obtain an expression for, again, I1 and I3 and I2 and I3. So you'd again have three variables in there, I1, I2, and I3. Again, plug in I1 and I2, reduce it, you only have two unknown variables. That makes sense to everyone. If we need more equations, we can apply KVL one more time, which actually is more efficient. Where else can we apply KVL? The big upper loop, so super mesh. But if you look at that loop, it has an advantage. What advantage does it have compared to this super mesh? M1 plus M2 plus M3 is also a super mesh. You could apply KVL to this. It is better than applying KVL to M1 plus M2. Why? Yes. Any guesses? Well, that's true, but yes. Yes, that's one of the things. You do have to worry about I1, obviously, but you only have three quantities, only three voltages. 1 ohm, 3, and 10. And then the follow-on would be it doesn't have any shared branches. The outer loop does not have any shared branches. Hence, it is the outer loop, is the big outer loop, does not share anything with any other branch. So the only unknowns you would have in there would be I1 and I3. That's it. You would have 1 times I1 plus 3 times I3 plus 10 equals 0. Simple equation, 3 quantities, that's it. Here you would have 1 shared branch, second shared branch. So more efficient, right? So in this case, sometimes I like to do this is even if I don't have a current source in there, it sometimes is easier if I just take the outer loop and apply KVL to that one. But again, it depends on the circuit. Depends on the circuit. Not always true, but sometimes it is. And depends on the circuit. All right, any questions? Any questions at all? Okay, then let me address homework. Last problem on the homework. How many of you have finished it? Everyone? Did anyone have questions about that? One before. Then we'll talk after class or outside of class. I still have office hours as usual. So we had 2 current sources in there. This is homework 10. And it's the last problem. I can't remember what the actual number is, but it's the last problem, number 6 on there. You have a resistor, you have a resistor. And here. Choose I1 clockwise, I2 clockwise, and I3 counterclockwise. The only reason I do that is because the current source is in the opposite direction. I was kind of overthinking this, but the current sources are not shared. So the important point here is if a current source in a circuit is not shared with any other mesh, you choose the mesh current which has the exact same direction as that current source. And you automatically have an answer for that mesh current. In this case, this was 1 amp. This was 2 amps. So I can write mesh current I1 is simply equal to 1. Mesh current I3 is equal to 2. And simply apply KVL in the middle mesh. 1 equation, 1 line answer, and that's it. Now, because this is simple, we don't have to worry about multiple meshes and writing the current equation. But because this resistor R3 has both currents going in the same direction, when you write the voltage for R3, VR3 would be R3 times I2 plus I3 and not minus. That comes because we chose I2 and I3 going in the exact same direction. So keep that in mind. If you wish to be consistent and you choose clockwise for all 3, that is fine. If you choose I3 to be clockwise, then it simply means I3 is equal to minus 2 amps. That's all it would mean. Okay. So sometimes an easier portion of the circuit of one mesh might make it more complicated in the other mesh. So in that case, again, it is your job as an engineer to figure out the most efficient method. Yes. Yes. Yeah, because the voltage drop would be plus minus plus minus. So when you apply KVL in mesh 2 in the middle, both currents are positive. If you applied KVL in mesh 3, then both currents would be negative. It would become minus I2 minus I3. So it gets balanced out. Yes. Well, when you have a current source in the middle of a circuit. So if it's a current source in the middle, then yeah, there's no way to describe the voltage across that current source. And so we'd apply. So anytime you're faced with a circuit and you cannot describe, and you apply KVL, but you cannot describe the voltage across that current source, that's when we would use the super mesh. Yes. Yeah, we have to. This one, right? No, that was just more efficient than doing the other super mesh. But we'd have to do one for I3 anyway. Mesh 3, we would have to apply KVL and find an equation in terms of I1, I2, and I3. So we need at least two equations, right? So we can apply KVL, this super mesh, or we can do this super mesh, or we can do this one. Any combination of those two. Yeah. Yeah. Yes. Okay. So again, we write as many equations as we need for us in order for us to solve for the unknown variables. It's the same thing with node voltage analysis. If you have two unknown variables, we need at least two equations. We don't need more. Same thing with mesh current analysis. Any other questions? Okay, so mesh current analysis is completely covered. Topic is now closed. Well, closed in the sense that the homework is now assigned and the due date would be Saturday. So before I finish for today, just want to talk briefly about superposition principle. If we go back and we look at the circuit, you have three voltages, VA, VB, and VC, right? VA, VB, VC. We found the current through R2, 0.15 amps going up. The 0.15 amps for the resistor R2, which is IR2, is a result of all three sources working at the same time. So we did mesh current analysis and we determined the current R2. Okay. Superposition principle states if you have more than one source in a circuit, you can break up the circuit into smaller pieces. Analyze each part or each piece individually with only one source acting alone. That means is, in this example, I have VA, VB, VC. If we are trying to find IR2, we would keep only VA active. VB and VC would be turned off, reduced to 0, and we would find IR2. Then we would find IR2 a second time for only VB working alone. Then we would find it a third time with only VC working alone. You'd have three values for IR2. IR2A, IR2B, and IR2C. Add up all three of those together, and you would obtain 0.15 amps, which is IR2. And that, in a nutshell, is the superposition principle. Basically states, if you have n number of sources in a circuit, you can break it up into n parts or n number of pieces. You analyze each piece independently or individually with only one source working at a time. and then you add up the values and you get the actual value for that quantity. Easy method, but highly inefficient, very laborious, and very time consuming, because you're performing 3 separate analyses for one quantity, right? You're trying to find IR2, you have to perform 3 separate analyses. If you want to find VR1, you have to analyze it 3 times just to find VR1. Then if you want to find VR2, you got to analyze it further 3 times, and so on and so forth. So again, easy, but very time consuming, highly inefficient. Okay, so we'll talk about this more on Friday. We'll go over the theory a little bit, and then we will look at an example, and then superposition homework. And I think only has 2 problems, if I remember correctly. And then that'll be assigned sometime, I don't know, maybe after Monday or so. Monday's quiz will be on mesh current analysis. Again, I will announce this on Friday and post the announcement on Canvas. But since we have completely finished the topic, letting you know in advance, mesh current analysis on Monday. If you have time, I might stick in a little bit of superposition also. But again, I will announce that on Friday. Final decision has not been taken. So we'll end class here today. I'll bid you a good day, and I will see you all on Friday. Office hours in the afternoon. I'll be available in my office if you have any questions. Yeah.